Look closely at any piece of solid metal, and you might think it is perfectly still. But down at the atomic level, it contains a violently fast, chaotic storm of subatomic particles bouncing rapidly inside a structured three-dimensional lattice. We can see the exact scale of this internal motion in these mathematical notes. This line identifies the thermal speed of free electrons at room temperature. They are moving at a staggering 10 to the 5th meters per second. Despite that incredible speed, this chunk of metal is not shocking you. That is because the motion is entirely random. For every electron moving left at high speed, another is moving right. Up cancels down. Their directional vectors perfectly negate each other, resulting in zero net movement of charge. Intrinsic thermal energy alone cannot drive a directional flow of charge. To break this perfect symmetry and actually create an electric current, an external forcing factor is absolutely required. That forcing factor is an applied electric field. When we apply a voltage across the metal, we introduce a strict directional bias to the system. With an electric field applied, the chaotic paths don't stop. Instead, the swarm collectively drifts slightly opposite the field. Notice the massive scale difference. Individual erratic paths are incredibly fast, but the net displacement vector, the actual progress, is minuscule. Returning to the mathematical definitions, we can quantify this shift. Look at the top section defining drift velocity. Its order of magnitude is just 10 to the negative 4th meters per second. This presents a fascinating physical reality. The macroscopic electrical currents that power our modern world rely entirely on an organized electron drift that is 1 billion times slower than their natural thermal speed. To understand exactly how that tiny drift velocity emerges from the chaos, we have to drop down in scale and analyze the mechanics of a single isolated electron experiencing an electric field. Electron acceleration is electric force divided by mass. Since electrons constantly crash into lattice ions, this isn't continuous. We define the velocity of an ith electron at time ti after its last collision, creating a kinematic equation linking its final velocity, initial state, and time. In this equation, ui represents the initial thermal velocity immediately after a bounce, while ti is the specific amount of time that has elapsed since that exact collision. Because every individual collision time and initial bounce angle is completely randomized, tracking a single electron is ultimately a dead end. We have to switch to a statistical bulk approach to find a meaningful average. To find the true macroscopic behavior, we apply a mathematical summation. We add up the velocities of n total electrons and divide by n to find the average across the entire swarm. Since initial thermal velocities are randomly scattered in all directions just after a collision, their statistical average is 0. The average time an electron travels between collisions is tau, the relaxation time. Substituting these gives our final drift velocity formula. This formula shows that the terminal drift speed is dictated by the intrinsic mass and charge of the electron, scaled entirely by the structural relaxation time of the specific metal lattice. Constant lattice scattering imposes a terminal velocity on the electrons, which prevents the infinite acceleration we would otherwise expect from a continuous electric field. Let's apply this to a cylindrical wire with area A. N represents charge carrier density per unit volume. The charge moving in time delta t equals the volume of a sliding electron cylinder, area A multiplied by drift velocity and delta t. These notes mirror that geometric derivation, defining the total electrons passing the cross-section. Multiplying by elementary charge E and substituting into the electric current definition, delta t cancels out. This leaves the final macroscopic equation, current I equals N E A V D. This proves that macroscopic current is strictly proportional to 3 physical factors: the microscopic drift speed, the physical cross-sectional area, and the specific electron density. This physical proportionality allows us to run a structural thought experiment. What must physically happen to the flowing electrons when a wire changes shape, but the total current remains constant? Because carrier density N and charge E remain constant, if current I is held constant, then area times drift velocity is also constant. Therefore, the area of section 1 times its drift velocity exactly equals area 2 times its drift velocity. We can visualize this abstract equation as fluid-like movement. As the wire narrows and the cross-sectional area drops, the individual particles must visibly accelerate, increasing their drift velocity to maintain the identical bulk flow rate. The strict continuity of charge demands that electrons speed up in constrictions. This perfectly links a macroscopic geometric constraint to a microscopic kinematic reality. Drift velocity tells us how fast electrons move under a specific field. But how do we standardize and compare conduction behavior across different materials, regardless of how strong the applied electric field is? We solve this by introducing a standardized metric called electrical mobility. As seen in the definition text here, mobility, represented by the Greek letter mu, is the ratio of the magnitude of drift velocity per unit of electric field. When we substitute our derived drift velocity formula into this new ratio, the electric field variable cancels out entirely. This leaves us with a measurable, standardized material property, with exact SI units of meters squared per volt second. Mobility strips away the external forces to reveal a pure, intrinsic property of the metal itself. It measures precisely how easily a material inherently allows charge to slip through its unique atomic lattice. We began with a seemingly perfectly still metal, only to uncover a violently chaotic thermal storm, moving at 10 to the 5th meters per second. By applying a field, we coaxed that chaos into a highly organized, but incredibly slow, 10 to the negative 4th meters per second drift. Every single amp of current measured in a laboratory or household circuit is merely the sum of trillions of these tiny, constantly interrupted subatomic steps. It is quite easy to take these macroscopic phenomena completely for granted when you only look at the final bulk result. By mapping individual electron collisions and averaging the results, we bridge the gap between macroscopic chaos and the predictable current equations we use to define real-world circuits.